In this lesson, we will look at the structure of control charts for variables and how they are used, and we will look at some of their benefits. And hello again to this lesson, which essentially has 3 learning objectives. What you see here is an example of a quality control chart. After this training, you should be able to name the main elements of such a quality control chart. Furthermore, you should have understood what warning and control limits are. You should know which causes can lead to a violation of these limits and which process characteristics should be monitored. Finally, you should be able to name the various benefits of quality control charts. This lesson is divided into 3 chapters. In the first chapter, we provide an overview of the various control charts and their characteristics. In the second chapter, we look at why and how the process spread and the process location is monitored. In the final chapter, we discuss some of the benefits of using quality control charts. Let's start with the different types and characteristics of control charts. This picture shows the relationship between the various characteristics and the control charts used. The different characteristics are shown on the left and the different control charts on the right. The quantitative characteristics shown on the left can be divided into 2 categories. First, the variable characteristics. These are all characteristics that can be measured. They always have a value and a unit. Examples of this would be the length, hardness, weight, surface roughness, or tensile strength of a component. Second, there are the attributive characteristics. Those are all characteristics one can only count, but we do not want to go into detail about them here. On the right, we have the different control charts for variable characteristics with a white background. These are also called Shewhart control charts, named after the American Walter Andrew Shewhart. As you can see, there are 3 control charts for monitoring the process location and 2 control charts for monitoring the spread. We will go into more detail about these control charts in a moment using some examples. What we see here is a simplified representation of a control chart. On the x-axis are the numbers of the different samples. In the simplest case, the sample size is exactly 1, but it can also include a group of 2, 3, 4, or 5 parts, and so on. The y-axis scale depends on the type of characteristic and its size. Examples of this would be the previously mentioned length of a part in millimeter or its weight in grams. The target value for a process is represented here by the middle line. Above and below this optimal process location are first the warning limits and then the control limits. There can now be 3 different situations in the process flow. First, as shown here, all values are between the lower and upper warning limits. This means the process is stable and no intervention is required. Second, values can be between the warning limits and control limits. This would be an indication that something is wrong and the process needs to be monitored more closely. It may even be necessary to increase the sample size. If values are then found between the warning and control limits, an intervention in the process might be required. As a third possibility, values could be outside the control limits. In such a case, immediate intervention in the process is required. Let's look at a more concrete example of a control chart next. Here we see a control chart for a sample size of 1. quality control charts can usually be divided into three areas. The top section contains general information about the product, such as the item number, part name, revision index, and so on. Other details, such as information on test equipment or characteristics of the control chart, can also be documented here. In the middle area is the graphical representation of the values with the scaling, the process limits, and the center line. Usually, there is also a lower area with the raw data of the measurements, or the values calculated from them, such as the mean, range, or standard deviation. Next, let's take a closer look at the warning limits and control limits. The warning and control limits are calculated based on existing measured values. These values can come from an already existing series production or from a pre-series carried out especially for the purpose of data collection. The following is now very important to understand. These limits are calculated in such a way that with the process under control, it is very unlikely that a value will fall outside these limits. If this does occur, this is an indication that the process is no longer under control. Let's now look at what probabilities we are talking about here and why you find different information on this. A value outside the control limits, as marked here, is an indication of an out-of-control process if no other special cause can be identified. Here we can see how small the probability is that a value is outside these limits. In the US, multiples of the standard deviation are used to calculate the limits. For the warning limits, this is twice the standard deviation. This results in a probability of 4.55% for violating a warning limit. 3 times the standard deviation is used for the control limits. This results in a probability of only 0.27% for a control limit to be violated. In Europe or the UK, the probability of violating the warning limits is set at 5%, and the probability of violating the control limits at 1%. You should remember that the probability that a control limit will be violated is in any case less than 1%, and that such an event indicates an out-of-control process that requires intervention. Here we see an example of an average control chart. Average charts are better suited for monitoring the process location than control charts for individual values. As can be seen in the table below, the sample size was 5 parts. The same characteristic was measured on each of these 5 parts, and the measured value was entered in the table. Then the arithmetic mean was calculated, and this value was marked in the diagram. For the limits, only the control limits at 60.088 mm and 60.112 mm were specified. Here we see an example of a range chart. The values are the same as those in the previous average chart, except that instead of the mean, the range was now calculated for each sample. The range is calculated from the difference between the minimum and maximum value and is a measure of the spread of the values. For small sample sizes like here, the range can be easily calculated. The standard deviation is another expression for the spread of values. It is used for larger sample sizes, in which case the calculation is usually automated. As we have seen, the process location is monitored using average charts. Process spread is controlled using range charts or standard deviation control charts. As we will see in the next section, both a shift in the process location and an increase in the spread can lead to products that are out of specification. This is the reason why both characteristics should always be monitored. This can be done in separate charts or in a combined average and range chart as shown here. Now that we have just done some work on that, let's talk a little bit more about why, for example, we monitor the averages and the spread. What we see here are three histograms. The x-axis is the scale for the measured value, increasing in size from left to right. The y-axis indicates how often a measured value occurred. If, for example, a specified length was measured on 10 different parts and the value 60.1 occurred 10 times, then the bar at the dimension 60.1 mm is 10 scale units high. LSL is the lower specification limit. This means the smallest still permissible size. And USL is the upper specification limit. This means the largest still permissible diameter. The first picture shows an optimal situation. The mean, this means most values, are in the middle of the specification limits. Because the spread is also small, all values are well within the specification limits. Such a process is not expected to produce out of specification parts. In the middle image, most of the values are still in the center between the two specification limits. However, the spread of the values has increased considerably. So much so that some values are outside the specification limits. An increase in the process spread has therefore resulted in products being produced which do not meet the requirements. In the third and last image, the spread is again very small, but the process location has shifted to the right. Also, here so far to the right that this shift has led to dimensions outside the permissible tolerance. Next, let's look at what this would look like in the value curve of a control chart. An ideal value curve of 200 values in a quality control chart would look something like this. The process location is in the middle of the specification limits and runs horizontally without jumps. The values only scatter slightly around the center. To better illustrate how the frequency distribution in the histogram is related to the value curve in the control chart, both images are superimposed here. The accumulation of values in the middle can be clearly seen, while only a few values are further away from the middle. Now let's look at what a variation in process spread might look like. The first 50 values have a relatively small spread. The next 50 values have a visibly greater spread. Samples 100 to 150 again have the same small spread as the first 50 values. With the last 50 values, however, the spread has become so large that even 3 values are outside the control limits. This would be a clear indication that the process is no longer under control and corrective action needs to be taken. A change in the process location could look like this on a control chart. The center line of the first 50 values is exactly in the middle of the two control limits. But the process location of the next 50 values has already shifted considerably. Although the spread of the values remained small, this shift in the process location was already enough for the upper control limit to be violated. Again, an indication that the process is out of control and corrective action needs to be taken. Changes in the process location and the spread often occur simultaneously and in every conceivable combination. That is why it is so important to monitor both process characteristics at the same time. Some of the advantages of quality control charts can already be derived from what has been discussed so far. Next, let's review what they are and what other benefits quality control charts offer. First, they are an early warning system. They indicate changes in the process results at an early stage. Second, they ensure consistent quality. The third thing to mention is their user-friendliness. They are relatively easy to maintain and can be filled out by the production staff themselves. They are easy to interpret. Warning and control limits indicate a need for action. Fourth, they make the process location and fluctuations in the process visible. In the event of unacceptable deviations, countermeasures can be taken in good time. Fifth, they serve as a means of communication between different shifts, process employees, process and quality managers, etc. And finally, they are an analysis aid. Special and common causes of fluctuations can be distinguished. A first important approach to solving problems in the event of deviations. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the three most important key messages. Control charts for variables monitor the spread and center tendency of process results. A value, a point, falling beyond the control limits indicate an out-of-control condition. A corrective action is necessary. And finally, control charts ensure consistent quality. If you found this lesson helpful, please let me know and leave a comment. Thank you for that. Take care and see you next time. Bye.